The derivative is to kinematics what the wheel is to travel. A simple yet very effective means for getting from one place to another. And to get just the right perspective of what else a derivative is, nothing works better than a little exercise. To begin with, a derivative doesn't apply only to a body in horizontal motion, nor for that matter, only to a body in vertical motion. Up, down, any which way, a derivative is the rate of change of any function at any exact point or instant. As illustrated by Galileo's law of falling bodies, speed is the derivative of distance. But it's more than that. A derivative can represent the rate of change of anything. For example, the population density of dolphins in relation to increasing or decreasing water temperature, or the rate of change in the volume of a balloon versus its surface area, or even the rate of change in the price of a pizza with respect to its size. Clearly, then, the concept of the derivative goes far and wide. But the mechanical process of the derivative, differential calculus, needs a practical approach, or the concept goes nowhere fast. Eventually, without the rules of differentiation, the simple concept of the derivative becomes an uphill struggle. In the long run, it helps to pick up a few more definitions along the way. So before it's too late to turn back, consider the factor of steepness. On the incline, the steepness is the ratio of the change in elevation to the change in horizontal distance. This ratio, a number, is called the slope. For example, suppose the elevation of an incline increases 15 meters every 100 meters. The rider moves upward 15, horizontally 100. The slope is 0.15. A hill with a slope of 0.3 is twice as steep as one with a slope of 0.15. The bigger the slope, the steeper the hill. When the slope is large, it's no small feat to get to the top. When the slope is next to nothing, near zero, it's easy going. And when the slope is negative, it's downhill all the way. Although mathematics can be easy going, it does have its peaks and valleys. And it always has. Nobody knows who first asked the best way to get from here to there. But the answer, in algebraic terms, was first offered by a French mathematician. Smoothly changing curve, there's a constantly changing slope. How then, in today's language, is a slope calculated at any given point? To determine the slope at a particular point, here for example, simply take another point on the hill. It doesn't matter where. Now connect the 2 points with a straight line. That line is called a chord, and its slope depends on the location of the second point. If the first and second points are reasonably close, the chord is a reasonably good approximation of the bike's path. Now, move the second point closer to the first. Move it even closer. The slope is a number, and as the points get closer together, the number gets closer to a certain value. It's reasonable to call that number the slope of the hill at that point. The line with that slope through the point is called the tangent line. And the tangent line is just what the chord turns into as the points get closer together. And the slope of the tangent line at that point is the slope of the hill. Instantaneous speed can be calculated along the same lines.
Oh no.
Galileo's law of falling bodies, applied here to a rather reluctant one, is more than an experiment in terror. It's differential calculus to the rescue.
Change in distance is divided by change in time. The ratio is the average speed during a given time interval. When that time shrinks to zero, the limiting value of the average speed is the instantaneous speed. Change in elevation is divided by change in horizontal distance. The result is the slope of a chord joining two points. When the horizontal distance shrinks to zero, the limiting value of the slope of the chord is the slope at that point.
Differentiation. The goals and calculations differ, but not the essential concept nor the process. Speed is the derivative of distance with respect to time. Slope is the derivative of elevation with respect to horizontal distance. In any case, a derivative is what happens to a quotient, a ratio of two numbers, as both top and bottom shrink to zero. Before they actually reach zero, small numbers are marked by the Greek letter delta. Delta y is a small change in y. Delta x, a small change in x. So delta y over delta x is merely a ratio of two small numbers. When the small numbers shrink to zero, that ratio becomes a derivative, and the deltas become a new symbol, dy over dx, the symbol of the derivative, which means the derivative with respect to x of the quantity y. Once the simple mechanics are mastered, finding the derivative for just about anything is no harder than flipping a switch.
The derivative of a function is the slope of its tangent at each point. The derivative of a function is itself a function. If the function is linear, the slope is constant, and the derivative is just that constant. If y equals sine x, then dy over dx equals cosine x. If y equals cosine x, then dy over dx equals minus sine x.
Taking derivatives takes a little practice, but it's well worth the effort. And considering any number of contemporary derivative machines, it's become a modern practice. A speedometer is a derivative machine. It measures the derivative of the distance traveled at each instant along the way. The rate of change of position is the instantaneous speed, expressed as miles per hour. Of course, when the vehicle isn't moving, no distance is being traveled. Here, the position is constant, and the derivative of a constant is zero. Mathematics is a language built on grammatical structure, a collection of rules that both builds and breaks down the composition of the task at hand. Whatever the masterwork, from building a house to composing a symphony, the most complicated task can be broken down in much the same way. Newton and Leibniz developed the tools of calculus that permit the most complex function to be differentiated by breaking it down into simple parts. One of the basic rules of differentiation is the sum rule. Suppose one painter can paint 90 square meters of wall per hour, and the other 100. Those are the rates at which areas of the wall are changing color. In other words, they're derivatives. Therefore, every hour, 190 square meters of wall are being painted altogether. That's how the sum rule works. The derivative of the sum is the sum of the derivatives. Another handy tool is the product rule, which is used to find the derivative of the product of two functions. For example, the area of any board is the product of its length times its width. If the length is shortened, the change in area is the width times the change in length. If the width is reduced, the change in area is the length times the change in width. The total change in area is the sum of these. That's true of the carpenter's product, and it's just as true in the language of differential calculus.
The derivative of the product y times z is y times the derivative of z plus z times the derivative of y. Using this rule, it's possible to find the derivative of x squared. Or of x to the third power, or of any power of x. The derivative of x to the power n is n times x to the power n minus 1.
Often, one operation is dependent on another. For example, suppose a vehicle has a fuel efficiency of 17 miles per gallon. That, too, is a derivative. If y is the distance traveled and x the amount of fuel consumed, then 17 miles per gallon equals dy over dx. Say it uses 2 gallons every hour. 2 gallons per hour equals dx over dt. A vehicle's speed in miles per hour is equal to the miles per gallon it gets times the gallons per hour it uses. This is the chain rule. It's used when y depends on x, and x depends on t. The sum rule. The product rule. And the chain rule. These three rules represent the grammar of differential calculus. and the value of differential calculus can be seen in the variety of its applications. For example, when a rocket moves with displacement s at time t, the derivative of the displacement is the velocity, positive for upward motion and negative for downward motion. The derivative of the velocity is the acceleration, which is the same as taking the derivative of a derivative. That is, the second derivative of s. The acceleration is caused